Hi everyone, I am Sandipan, and the topic of my presentation is stellar parameter estimation through spectroscopy. So throughout this presentation, I will first explain what a stellar spectrum is, what are the parameters which affect that spectrum, how can we infer those parameters, and what is the role of spectroscopy in studying star-planet systems, which is also my PhD topic. So stellar spectrum is just a spectrum of the star's atmosphere. Uh, but is it a black body spectrum? Well, no, because there are absorption by different elements. And the strong lines that you see here are from the hydrogen, and the weaker ones are from the excited and ionized atoms. So the next question which arises is what affects those absorption lines? Well, if you look at the Boltzmann equation, which gives you the ratio between the population density between two excited states, then you can see that it depends on the ionization energy and the temperature. Well, for ionization energy is just the energy difference between two energy levels, so we can determine it through experiments. And the temperature is what is affecting here. So one of the parameters which affects the absorption line is the temperature. Well, temperature also causes thermal broadening because of Doppler motions. So if the particle is moving randomly, it will emit, the light will be blue or red shifted accordingly, and it will broaden the absorption lines. The next thing which is governing our system is the Saha ionization equation. So basically, it explains the population density between two ionized energy levels. And that depends on temperature as well as on the pressure. So we have now two parameters, the temperature and pressure. But well, the pressure is affected by the surface gravity. Surface gravity is just the acceleration due to gravity at the surface of the star. So instead of pressure, we use surface gravity as a parameter. Pressure also causes broadening, and it is due to collision with neutral atoms or ions. And the profile that you see here in red is from the collisions in the star's atmosphere. The blue one is the profile that you see of a absorption line from the thermal broadening. Well, if the star is also rotating, then the lines will again get broadened because of Doppler shifts. As you can see in the right-hand side, one part of the star will move towards you and the other part will move away from you. And through that, the line will again get broadened. Next is the radial velocity. So if the star is moving towards you or away from you, that will just shift the whole spectrum, either redshifted or towards the blue. Next is the micro turbulence velocity. And yeah, it's a bit confusing what it actually is. Well, it was introduced to compensate for thermal broadening and collisional broadening. So there were lines which were observed, and they were not, people were not able to explain how those lines get broadened just by using thermal and collisional broadening. So they have introduced another velocity which they call microturbulence velocity. And these are explained to be small turbulences in the star's atmosphere, which behaves a bit similar to thermal broadening, but it can be different. So this is another parameter that we have to include to understand absorption lines. Next is the abundance of elements. So, well, if you have more elements, then there will be more absorption. If you have less, then it will be less. So if you see the blue lines, specifically the iron lines, then you will see that if I change the iron abundance, then those lines will get much sharper, but the other lines will not get affected here. Next is your resolution of the spectrograph. Well, if your spectrograph is good, then you will get sharper features. And if you have a bad spectrograph or a low resolution spectrograph, this broad you will have these broad lines. Another effect is from the transition probability itself. So For each line, the atoms which are present, they have a specific probability of transition between two energy levels. It is not one. And the transition between two energy levels has a specific probability associated with it. If you increase that probability, then the line strength will increase. If you decrease the probability, it will decrease. But the resolution and transition probability cannot be calculated directly from the spectra. It's not calculated, but yeah, the resolution you know it from your instrument manual, and the transition probability you can know it from either experiments that were done by other atomic physicists, or in some cases from the sun. So finally, we are left with these parameters that we can estimate from the spectrum. It is the temperature, surface gravity, the rotational velocity, radial velocity, microturbulence velocity, and abundances. But what we see here is that we only need the absorption lines for our analysis. We don't need the continuum. So the continuum is this broad feature that you see here, which looks like a black body. We don't need that for the analysis. So what we can do is remove the continuum. But the question now arises is, how can you decide where the continuum is? What you can do here is take a small window in the wavelength range, a small window in the wavelength, take an average of the flux values and move that window over the whole spectrum. As you can see here, when you do that, you will get these black dots, which are the moving averages of the and which traces the continuum quite well. But there can be dots which also moves through the absorption lines, and we don't want that because we just want to remove the continuum. So we have to remove that part where the dots lie on an absorption line and then fit it again. This is one of the way where we can determine the continuum, but there are a few bit of manual labor involved. Another thing that you can do is what's called an asymmetric sigma clipping. Here you, like previous, you take a small window, you determine the average flux there, but instead of denoting that average flux as the continuum, what you do is remove all the flux values which are 1 sigma below the average, and you remove all the fluxes which are 3 sigma above the average. So if you see here on the right, it will take all these data points which are between 3 sigma above the average, and take all the data points which are between the average and the 1 sigma. So as you can see, there is an asymmetric choice here, and that will remove these absorption lines from the spectrum. If you can see in the GIF, you can see that after a few iterations, it will start tracing the continuum quite well, and you can use this to remove the continuum. And below is something what's called the continuum normalized spectra, which we can then use for further analysis. Now, how do we estimate those parameters? The idea is simple. You have to just take a synthetic spectra from models and then fit the spectrum to the observations. But how? So, well, there are a few ways. One is to use the Balmer lines. Balmer lines are just the hydrogen lines, where the electron transits from the second energy level to higher energy levels. The good thing about using a Balmer line is that it does not get affected by the rotational velocity, the microturbulence velocity, or the resolution. That's only because the Balmer lines are so broad that even if you increase the rotational velocity or the resolution by a few, it will not change at all. But the problem with Balmer line is, since it is too big, it is difficult to normalize around. It is difficult to remove the continuum around the line. Here is a plot of a here is a plot of a Balmer line. As you can see in the lower part here, the Balmer line can be divided into two parts. One is called the wing and another is called the core. If you look at the right-hand side of the first column, these are the hydrogen Balmer lines at the transition from n equal to 2 to n equal to 3, n equal to 2 equal n equal to 2 to n equal to 4, and n equal to 2 to n equal to 5. So these are the transitions that takes place and are called Balmer lines with alpha, beta, and gamma. And if you change the temperature, you see that the wings of the Balmer lines change quite a bit. But remember, the temperature is around 6000 Kelvin, where these changes can happen in temperature. But if you change the surface gravity, you see that the wings of the Balmer lines does not change much. But now if we go to a higher temperature star, let's say around 10,000 and above, then you see that the continuum is getting affected more by the surface gravity compared to the temperature. So what I want to say is, through the use of these Balmer line wings, we can determine the temperature and surface gravity of the star. How good the estimates of both those parameters depends on which temperature regime you are working on. Here is an example of a fit of the star HD 21997, and you can see that we are getting quite a good fit, but the temperatures and the surface gravity are a bit different, but not too much. But that's okay, because there can be several factors which are affecting it. One is the normalization around the Balmer lines, and another is how much noise there is in the spectrum. Next is, after analyzing the Balmer lines, we are left with the metal lines. So metal lines are the absorption lines from all the elements that are present in the spectrum, except for hydrogen and helium. There are two methods of estimating parameters through metal lines. One is called the spectral fitting method, and another is called the line-by-line method. For spectral fitting method, which I currently work on, you have to choose small wavelength regions in your spectrum. Here I have chosen, let's say, 4 regions where you think that there are metal lines which are above the noise level and which covers a wide range of ionization and excitation levels. So once you select those wavelength regions, you approximate the radial and rotational velocity of the star. In our case, the radial velocity was quite close to 0, and the rotational velocity was around 50 kilometers per second. And you also approximate the temperature and surface gravity. And for that, we can use the Balmer lines estimates that we previously measured. Well, once we have the estimates, we just have to fit the whole spectrum. And once you fit it, you will get certain values of temperature, surface gravity, and all the velocities. But you have to iterate it over a few times to get the values to converge basically. So once you get a converging value, you are sure that these are the parameters that you have from this star. There can be a possibility that there are degeneracies involved between two parameters, which can happen mainly in temperature and surface gravity. When you have that, and that can be an issue, what you do is you look for other methodologies. Like we have the analysis from our Balmer lines. We have the analysis from our metal lines. We can also have analysis from photometries. And through that, you will get a sense of where your temperature and surface gravity lies. And through that, you will get a more consistent parameter values. The another methodology that can be used for analysis of metal lines is called the line-by-line method. Here, you assume a temperature, surface gravity, and all the velocities to have you take an initial value. Next, you plot the abundance of the, let's say, iron in this case, with the excitation energy. So each of the data points that you see here represents each of the data points that you see here represent one of the absorption lines of the iron. So by fitting that iron line and determining the abundance based on the initial parameters that you have, you will get a certain plot. If you see that there is a positive slope between the iron abundance and the excitation energy, you are sure that there is something wrong, because for a star you need to have just one abundance of the iron. You cannot have multiple abundances. Why this happens is because if there is a temperature which is a bit low, then you will find that the transitions which require less excitation to jump will have more strength. The line will have more strength. And to compensate for that strength, the abundance will get lower. And if the excitation energy is high, the transition strength will be low. And to compensate for that, the iron abundance will get high. So you will get this positive slope if you have a low temperature estimate. So what you need to do is iterate over a few times till you get a slope of 0, and you are sure that this is the temperature of your star. To estimate the surface gravity, you can do a similar thing, but as I said, the surface gravity affects the ionization states of an element. So instead of determining abundances of just one excited state or an ionized state, what you do is determine the abundances and take the difference between two ionization levels. Once you do that, and you do that for different surface gravities, you will get a plot like this. And when the difference between the abundances is 0, you know that that is a surface gravity that you are looking for. But the problem is, when you are measuring the surface gravity, you are assuming a temperature based on this previous estimate. But now the surface gravity that you got may be different from what you have assumed in this previous plot. So now you have to iterate it over and take the surface gravity that you got from your previous estimate to get the temperature again, and use this new temperature to get the surface gravity again. So you have to iterate it over a few times until that process converges. Next, if you want to estimate the microturbulence, what you can do is you can plot the abundance versus the equivalent width of a line. Equivalent width is just the area under the spectral line, and it is explained as the width of a rectangle in wavelength times the intensity, which in our case from 1 to 0, which will just be 1. So the area of this rectangle and the area under the spectral line should be the same. So, and the width will then be, the units of this width will then be in wavelengths. So it basically denotes the same thing, it's just the area of the spectral line. So when you plot the abundance versus the equivalent widths, the microturbulence affects this area under the spectral line. And the effect will be different depending on the strength of the line. If the line is weak, the effect of the microturbulence on the area under the spectral line will be low. Whereas if the microturbulence is high, whereas the effect of the microturbulence at strong absorption lines will be high. So what you can do is you can take a range of absorption lines of iron with the very broad ranges of equivalent widths. In that way, you are sure that these effects are taken into account. And you again do the same thing. You want to get the slope to be 0 because, again, you don't want the iron abundance to change with the area under the spectral line. So once you have that, you will get the microturbulence. But again, we are assuming here a specific temperature and surface gravity based on our previous two estimates. So you have to loop it over again. You have to give this microturbulence values to estimate the temperature again, and you have to iterate it a few times until these values converges. Once you have that, once you have all those parameters, we are only left with the abundances, and we can estimate those abundances again by fitting just the spectra. Okay. Uh, okay, so, but how does it relate to my work? What I'm working on is called the star-planet connection. The idea is simple. If there is a planet which is rotating around a star, and that star also has a protoplanetary disk around it, the planet which is moving around the star will sweep away all the gases and dust present in its particular circumference. So you will see that the density at that particular radius will be low, and in other places it will be just the same. So what will happen due to this gap in the disk, the dust particles which are present.
Oops.
The dust in. Hello.
Yeah, you are.
Uh, am I am I connected or?
Yeah, you were disconnected slightly, but now we can hear.
Okay. Sorry. Yeah. Okay. Well, dust are heavier than gases, so they will get a drag force because of which they should get accumulated on the star. In that way, we do not expect to form any kind of planet around a star at all. So what we need is that the dust should somehow get trapped somewhere on the protoplanetary disk so that you can get planetesimals and then a planet. So my problem is not directly related to that, but if there already exists a planet, then the gases present near this position where there is a gap will be depleted. So the dust grains will not feel any drag force. If there is no drag force, the dust will just get accumulated at this region. And if that happens, you will see a bump in the dust density. And if that happens, those dust grains will coagulate and start forming planetesimals, and it is expected that it will also form planets later on. Well, the dusts are specifically formed by refractory elements, whereas the gases are formed by volatile elements. Refractory elements are those elements which can condense at a higher temperature, and volatile elements condense at a lower temperature. So we are seeing here that the dust should get trapped here, whereas the gases can freely flow. So if that happens, then the accretion on the star would allow the allow to change the surface composition of the star itself, because more of the volatile elements are getting accreted compared to the refractory elements. And if that happens, we should be able to see the changes in the abundances of the elements at the stellar surface. These changes can only be seen for hotter stars where there is a radiative envelope, specifically because the mixing of the uh, matter at the surface will be quite slow compared to a star which has a convective envelope. Yeah, thank you. I'm done.
Okay. Questions? Comments? Denis?
I have a kind of technical question. You showed this continuum normalization, and I think using this asymmetric sigma clipping.
Yeah.
That how well this algorithm can take care of imperfections of, for example, a shell order merging and some sudden jumps that look very much the same as some blended spectral lines.
Um, from what I have tried, unless those jumps are quite like if they're not quite that instantaneous in a way in wavelength, then it can trace the jumps. But yeah, it can be difficult if those jumps are quite strong. That's it. But I think in general, I tried it with HARP spectra and it works. And yeah, I haven't tried with much yet.
Yeah, it's quite common to have them in the order of 1, maybe even 2%. And it doesn't sound like a lot, but it's really a problem if you want to estimate those parameters really accurately. And
Yeah.
I have one comment as well. You mentioned that the hydrogen lines are not affected by V sin I, and what was the
resolution?
And resolution. This is very far from truth. This is only if you are talking about very high resolution spectrographs and very slowly rotating stars.
Yeah. At least the data I worked with, I didn't see much effect, so I could use it even assuming a V sin I of 0. But yeah, maybe if the rotational velocity is quite high, then yeah, it will affect.
If you will work with massive star, for example,
this is the norm.
Yeah.
Yes.
Okay.
So you cannot tell that it will not affect. It will affect.
Yes, really a lot.
And also, if you are working with a spectrograph with a resolution 10,000 versus 100,000, then it also the difference will be quite large.
What 10,000? 100 versus 100,000.
Yeah, something like that.
100, you barely see hydrogen lines, but you see.
So this is just it. What you said is not wrong. It is just limited to specific type of star and spectrograph. That's it.
Okay. Yeah.
Any more questions, comments? Those who are online can either speak up or just write the chat so we can see it.